Hi, welcome to the 8th week of video lectures. So, in this course Digital Circuits and Systems, we are getting towards the end. So, upfront I want to tell you that there is some material that has not been covered so far, and there were a few emails on the forum. So, things about number representations and about arithmetic circuits. So, I decided to actually take one more week to cover that. So, this week is not the last week in terms of videos. So, there will be one more week in which I will cover basic arithmetic circuits as well as number representations. So, this is the last but one week. So, we are in the 8th week now, and in this week what we will look at is an interesting topic called pipelining. So, pipelining has a lot of, we do a lot of things in the real world which are actually pipeline. We never call them pipeline though. We will take a real world example of that sort, and we will see what is the inspiration in digital circuits to make them faster. So, this is a very important topic, and this is usually not covered in at least second year undergraduate material. This may be covered in either fourth year undergraduates or in the first year graduate level, but it is a very useful technique to know, and if you understand this well, you will be able to understand processor design. If you are going to take any course on CPUs and how they are designed, this is very useful. So, the material for part of the material for this week's videos are actually taken from this course from MIT, and this is called computational structures. The course number is 6.004. So, MIT in the US has been offering a course on computational structures for a long time under what is called open courseware, or OCW they call it, and so they allow professors and others to use this. So, it is under what is called Creative Commons license. So, if I attribute to it, and as long as I am not using it for commercial purposes, and whatever material I am making, as long as I share it with others, MIT's license allows me to do that. So, I am going to use some of the material from the computational structures course to teach this. So, let us now look at a real world problem. So, let us say we have laundry to do, and the laundry typically requires you to wash and dry them. So, let us say I have two different machines. I have a washer. The washer needs to fill up, needs to agitate and spin, and let us say washer's propagational delay is 30 minutes. So, it takes about 30 minutes to wash clothes. Dryer on the other hand is a separate device, is available as a separate appliance. You can buy a dryer, and there are dryers which will spin and even apply heat to it, so that when you get the clothes outside from the dryer, they are already dry. You can fold them and put it aside. You do not even have to hang them for drying. So, these appliances usually take more time. Let us assume that the dryer takes 60 minutes. So, this is typical of a washer and dryer combination. So, in India, when we usually buy dryers, they do not dry them completely. So, they are still wet and you have to hang them in clothes and so on, but there are these appliances available where you can actually dry it. It will come out hot, and all you have to do is just fold and keep it aside. So, we have a washer which takes 30 minutes, and we have a dryer which takes 60 minutes, and let us see how notion of a laundry, if you want to wash clothes, how it can get done. So, if we do one load at a time, then what we can do is we can load the clothes. When we load the clothes in the washer, it is going to take 30 minutes, and during that time, let us say I have this dryer also, the dryer is not going to do any work. So, when the washer is washing, the dryer is not doing any work, and once the wash is over, I have to take the clothes from the washer, put it in the dryer, that is in step 2. So, when the clothes are drying, the washer is not really doing anything. So, clearly this is not a smart thing to do. So, if I have one load of clothes, I have only one basket of clothes I have to wash, then for 30 minutes I will wash, and for 60 minutes I will dry, but when I am washing, the dryer is not used, when I am drying, the washer is not used. Right? This is okay if I have only one load, but if I have, let us say 5 loads of clothes that I want to wash, not using the washer and dryer is not sensible. So, it is not a very smart thing to do. If I take one load at a time and I use only the washer and then only the dryer and so on. We will see how this is related to circuits in a little while, but let us take this real world example to its logical conclusion. So, the first thing we will note down is the total time taken is the propagational delay of the washer plus the propagational delay of the dryer. So, that is the 30 plus 60 minutes, that is 90 minutes. Let us say I want to do n loads of laundry. So, I have some number n, and if you want to do it in what is called the combinational way or the non-smart way of doing it, I have so many clothes, and what I will do is in step 1 I will take one of these laundry baskets, wash it, that will take 30 minutes, then I will take those clothes which are washed, put them in the dryer, that will take 60 minutes. So, in 90 minutes one load is done. Then in the 90th minute I will take the second load, put it in the washer, that will take 30 minutes. So, 120 minutes overall, plus another 60 minutes to dry the second load. So, in 180 minutes I will finish 2 loads. So, if I want to finish n loads, then I will take n into 90 minutes. So, the combinational way of doing it, so each wash and dry cycle takes 90 minutes, and I have n of these loads. So, overall I will require n into 90 minutes, and you can see the problem here at any point of time. So, I have one single washer and one single dryer, but when the washer is in use, the dryer is not being used. When the dryer is in use, when the washer is not being in use. So, in the real world, if you had n loads of clothes, you would really not operate it this way. Would you? Would you think about using only the washer or only the dryer? So, you would think about when the washer is washing, you would put clothes. So, when the first load, dryer cannot run, so you will wash it, and as soon as the wash is over, you will put it into the dryer. Now, the washer becomes free. So, in step 2 the washer is free. You can technically go and put another load inside, right, and this will take 30 minutes to finish, but overall this is going to take 60 minutes. So, by the time you wash 2 loads of clothes, you would have done only 1 load of drying. So, you need to wait for the dryer and then put it and so on. We can figure out how to do these things, but clearly taking only one wash and one load at a time, one wash and one dry at a time, and not using the other one does not make sense. So, the smart way to do that is doing what is called pipelining. So, the way the pipelining would work is, ideally we would like this. So, initially the dryer is not being used, you take the first load and put it inside for wash, and that takes 30 minutes. Whenever it is done, take it and put it in the dryer, and take the second load and put it in the washer, and whenever the dryer is ready and if the clothes are washed, you take the wash, put it in the dryer, take a new load and put it in the washer, and so on. So, doing something like this is called pipelining. So, this pipelining is something that we do in the real world more often than we can imagine. So, if you are cooking, for instance, you do the same thing. So, when you are so maybe you put something on the stove, but then you are cutting some vegetables, you are boiling the water also, and so on, right. It is not that you do all of these steps sequentially. So, when something is cooking, you go and prepare something else, and when that is cooked, then you move that to the stove and you start preparing for the next dish and so on. So, that is also actually an example of pipelining. So, pipelining is a smart way of doing activities, and what pipelining gives you is, it gives you 2 things. One, these units are going to be busy. We are not going to underutilize the washer or the dryer. So, in 90 minutes, if I use 30 minutes for washing, 60 minutes for drying. So, in 90 minutes the washer is not used for 30 minutes and the dryer is not used for 60 minutes. So, it is not an effective use of the appliance. Imagine I have to rent the washer and dryer, I want to get as many loads as I want, clearly you would not do it this way. So, that is one thing that you get from pipelining. The second thing from pipelining that you get is, if you have n wash and dries that you have to run, then it reduces the amount of time that you need for doing this. So, let us see what it will take. The total time it will take is n times, not the summation of washer plus dryer, but the max of washer plus dryer. So, the one that is constraining the load to go is, washer anyway gets done in 30 minutes, the dryer takes longer time. So, for every load, so let us look at this. The very first load will take 30 minutes, and once that 30 minutes is over, I take that and put it in the dryer. This is going to take 60 minutes, but meanwhile I can get another load washed, right. So, I wash it now. So, the maximum of these 2 tasks is going to take 60 minutes, right, and that is what this max is. So, max of washer and dryer is 60 minutes, it is n into 60. So, overall you will require something which is n into 60. So, this is actually an approximation. Technically you actually need n into 60 minutes plus the 30 minutes for the very first washer when there is no drying that is happening. So, you still need to spend that 30 minutes. So, I suggest that you go and work this out. So, what we are doing is at any point of time we keep one wash ready. So, there are lots of loads of clothes that we need to wash at any point of time. If we want one of them ready for the dryer, and whenever the dryer is ready, if you want to put it for wash, put the wash clothes for drying, that is the setup that we have assumed here. This will require n into 60 minutes plus 30 minutes. So, in the steady state, if I have an infinite supply of inputs, then n into 60 will be much greater than 30. So, saying that the total time taken if you have a pipeline system is n into 60 minutes is okay. Imagine n being 10, 20, 100 and so on. If I want to wash 100 loads of clothes, this 30 minutes is not a big deal. The very first 30 minutes that you use when the dryer is not being used is not a big deal. So, n into 60 is a good enough approximation. We can forget the fact that we took another 30 minutes in the beginning. So, let us look at the so called performance measures that are relevant to pipelining. There are two measures that are relevant to pipelining. One is called latency and the other is called throughput. Latency is defined as the delay from when an input is established until the output associated with that becomes valid. So, essentially for our cloth washing example, the latency is if I have some unwashed load of clothes, it will need at least 30 minutes for washing and 60 minutes for drying. So, it will take 90 minutes. So, the latency if I do it combinationally, it is 90 minutes. Whereas, if I do it in a pipeline manner, let us go back to the picture. So, if I take a load, then I put it for wash, which takes 30 minutes, but if the dryer, let us say I start wash and dry at the same time step, at time step 2 I have taken the first wash and I put it here, and I have taken a new load and put it for wash. Right. When I have done that, then this wash will actually get over in 30 minutes itself, but we are waiting for another 30 minutes so that the dryer is ready. So, I have already spent 60 minutes in some sense, for 30 minutes for washing and 30 minutes for waiting for the dryer, and then another 60 minutes for drying. So, which means the latency in the pipeline setup requires 120 minutes. So, the assumption is that wash is started as soon as possible and waits in the washer until the dryer is available. If you are allowed to take the wet clothes out, you can actually load it with another set of clothes. So, we are assuming that the wet clothes remain in the washer itself till the dryer is ready. So, if we make that assumption, then the pipeline system has a latency of 120 minutes. So, latency is from the time when you started the work, how long did it take you to finish the work. So, that is called latency. So, the pipeline systems may add to the latency of the work. So, instead of 90 minutes, we have taken 120 minutes. So, a single load of clothes may take more time to wash, but what you get from a pipeline system is higher throughput. So, throughput is defined as the rate at which the inputs or outputs is processed, right. So, let us look at this. For the combinational setup, once every 90 minutes you get an output. So, you wash and you dry, and once every 90 minutes you get a load, right. So, the combinational throughput is 1 over 90 outputs per minute. So, on a per minute basis if you ask, then I can say that 1 by 90 loads are getting done in every minute, right. So, even though it takes 90 minutes to produce the first load, just like measurement, it is just a rate, right. So, the rate at which the loads are processed is 1 over 90 outputs per minute, whereas in a pipeline system every 60 minutes you are ready to take the next load, because so you will move from the washer to the dryer, the washer becomes free, you can take the next load and put it. You know that in the next 60 minutes the dryer will become free, you can take the wet clothes, put it in the dryer, the washer again becomes free and so on. So, for every 60 minutes I can go and put a new load of clothes in. So, the throughput on the pipeline system is more than that of the unpipelined system or the non-pipeline system. So, the pipeline system is able to process 1 over 60 outputs per minute. So, it is going to give, so 1 over 60 is larger than 1 over 90. So, the throughput of the pipeline system is better than the throughput of the combinational system. So, let us get back to circuits. Let us say I have a circuit like this. I have X, which is an input, and I have two inputs F and G, which they go to H. So, assume that F, G and H are all combinational to begin with. So, what we are getting out of the circuit P of X is some composition H of F of X and G of X. So, H is some function. So, you can think of it as F is some AND gate, this is some OR gate, that is some XOR gate or something like that. Let us assume that all these are combinational blocks. Let us see how this whole thing works. So, you provide X, which is an input to this system. F and G are going to take their own time to process X. So, F of X takes some time, and in this example let us assume that this combinational block G is going to take more time. So, you have G. H can process only after F and G are both steady state. So, you wait for both of those. So, this is the time taken by H. Once F gets settled down and G gets settled down, then you have to wait and only then you can process H. So, for combinational logic, the latency that we have is the propagation delay itself. So, let us again look at this picture here. So, once I place X, F of X is going to get ready after some time, and since G is taking a little more time, so it looks like G is getting ready only at this time point, and at this time point F and G are both ready. So, H has some finite time and only then you process, only then you get output. So, in terms of delay, what we have is maximum of F and G plus H, that is the time that it will take. So, if this is 2 units delay and if this is 3 units delay, and let us say H is 5 units delay. So, F will place the, so if X will get transformed in 2 time units, it will be available here. G, however, will take 3 time units. So, I have to wait for the latest or the one which is coming late. So, F of X is coming earlier than G of X. I have to wait for G of X, and then H will take F of X and G of X and take some amount of time and process it and send it out as P of X. So, the latency in combinational logic is whatever the propagation delay is, and you know how to calculate the critical path. If I give you 2 blocks like this and if I give you another block like this, you know how to calculate the propagation delay. We did this in week 6. So, if you do not remember it, go back and review the videos in week 6, we did this. So, the latency is the time at which X became steady to the time at which P of X became available. So, it is the time difference between this period from here all the way up till here, that is the propagation delay. The throughput is, I can, once I give these inputs, I have to wait and keep the input steady till the output becomes steady, which means I can only give one input every latency, whatever the latency is. So, 1 by the propagational delay is latency for combinational circuits. We cannot get a faster answer than the latency that is given, and the number of inputs I can give to this whole chip is constrained. So, I can only give so many, I can only process as many as the latency will allow me to. So, the question is, are we using this hardware effectively or not? So, let us see if we want to do it as a pipeline circuit, we are going to use registers and keep the input stable. So, in this example what is done is, we are assuming that F takes 15 units of time and G takes 20 units of time, H takes 25 units of time. So, in the non-pipeline version, the H will have to wait for the one whichever is delayed, F or G. So, it is 20 time units that G takes plus 25 time units that H takes. So, you have to wait for 45 time units. If I place X, the TPD in the combinational setup is 45 time units. But when you do pipelining, what you do is you place what are called registers. You put registers here, here and here. So, the moment you do that, if I go and look at the rate at which the inputs can be given, if I go and look at the flop to flop delay, the flop to flop delay is 25 time units, because in this flop to this flop is 25, this flop to this flop is 25, both of them are 25, so the maximum is 25. And if I assume, so if I go and look at the input to flop delay, that is 15 here, that is 20 here, so the maximum of this is 20. So the input to flop delay is 20 time units and flop to flop delay is 25 time units. Because this flop to flop delay is greater than the input to flop delay, I cannot give any inputs any faster than the flop to flop delay itself. So I can keep giving inputs every 25 time units. So if I bring in an input at time unit 0, at time unit 15 it will be available here, at time unit 20 it will be available here, but to the system I am going to give 25 time units. So this is equivalent to the wet clothes that are waiting in the washer itself. So they wait here, at the 25th time unit they get registered, right, because the clock pulse comes in. Then when the clock pulse comes in here, it will take 25 time units to go to this register. Meanwhile, you can place the next set of inputs here, which will take 15 or 20 time units to process. They will wait here till the next clock pulse comes in and takes these inputs. So what we are doing is, we are essentially, when you pipeline a circuit, we are making effective use of the hardware. So when H is working on Xi, so if I give X at time unit I, let me call that input as Xi, this is the 5th input or the 7th input or the 9th input and so on. If H is working on Xi, F and G are actually going to work on Xi plus 1. So if H is processing the 5th input, then F and G will be processing the 6th input, and P of X will be the 4th input's output, and so on, right. So when H and G are working on Xi, F and G will work on Xi plus 1. This so if we go back to the laundry example, when I am drying the 3rd load, I can wash the 4th load and the 2nd load is ready outside, right. So that is the analogy here. So here you will have Xi minus 1, this is Xi, this will be processing Xi, and F and G will be processing Xi plus 1. You cannot give Xi plus 2 at this point of time. So this setup is called a two-stage pipeline. It's called a two-stage pipeline because there are 2 stages to the moment I place the input, it goes through 2 stages, one stage which is here and another stage which is here. So this is called a two-stage pipeline. If I go and look at the number of flip-flops that X has to encounter from going from X to P of X, through this path it requires one flip-flop stage and another flip-flop stage here. So it's 2 stages. If I come from here, it takes one flip-flop stage and another flip-flop stage. This also requires 2 flip-flop stages. So this is called a two-stage pipeline. A valid input at X in clock cycle J will get will get P of X in cycle J plus 2. I already mentioned that. So if you assume that all the flip-flops have 0 delays, then the unpipelined latency will be 45 time units. So it's maximum of 15, 20 plus 25. So it's 45 time units. So the throughput is 1 by 45. A two-stage pipeline, however, will have a latency of 50 time units, because even though this gets ready in 55 or 20, you wait for this extra time period to the clock pulse to come and register here. So here you will have 25 time units of processing, here you will have 25 time units of processing. So overall the latency is 50. If I give an input here, it will take 50 time units for P of X to be ready. So the latency has increased, however, the throughput is every 25 time units I can give a input. So it's 1 by 25. So earlier we had 1 over 60 loads per minute. Here I can give 1 by 25 inputs per minute, or inputs per time unit. I can give 1 by 25 inputs per time unit. So the latency, even though it increases, the throughput of a pipeline system reduces. So one thing that we have assumed is, we have assumed that the flip-flop itself has 0 clock to Q delay, and the internal delays are 0. We assume that this 50, 20 and 25 are enough to satisfy the setup time constraints on these flip-flops. We have assumed that the flip-flop is essentially a 0 delay structure. So when you do this, we can construct what is called a pipeline diagram. what you have in the x axis is time units or the inputs. So, this is input I plus 1, input I plus 2 and input I plus 3 and so on, right. So, the x is the input, so that is what you see here. So, xi is input given at time period I. The f register and g register can only get f of xi and g of xi at time I plus 1, and this will be placed as input to the combinational logic H. So, H will take at the end of time period I plus 1, H will take f of xi and g of xi and produce and it will produce h of xi. So, if you notice this pink diagonal here, this xi is input given at time I. At time I plus 1, f of xi and g of xi will be ready, and at time I plus 2, h of xi or p of xi is ready. So, however, at I plus 1, I can place the inputs xi plus 1, they will get ready at I plus 2 for h to take in, and h will produce the output at I plus 3. So, this yellow one is the second set of input, and the violet one corresponds to the third set of inputs. You can think of this as, this is the unwashed clothes, this is the washer, and this is the dryer, right. So, in the washer and dryer example, we did not have f and g, there was only one washer, there was one f and one h, whereas here we have a f and g, there are two blocks, two combinational blocks. So, the results related to a particular input moves diagonally across the pipeline diagram, and the process inputs progress through one pipeline stage at a time. So, from the external input it goes to stage 1 and then goes to stage 2, it gets out of stage 2 at time step 2 away, and this goes through one step at a time. So, this kind of a pipeline diagram is useful to imagine what is happening in the circuit. So, this brings me to the end of this module. In this module, what we saw is the notion of pipelining. So, the term pipelining is used to specify this fact that we do not have to waste our time waiting for some other stage to finish the work. When the next stage is doing some work, you take the previous stage and give it some more work, and this keeps happening in lockstep fashion. Eventually, what you have is the latency of a single input to go through the pipeline stages may increase, the amount of time may increase. However, the number of inputs that you process per time unit improves, the throughput improves in a pipeline system. We will see the ramifications of this latency and throughput in the next video. So, this brings me to the end of this module.